Good afternoon, everyone. Thanks for being here today. Today I will be presenting this sixth lecture on reinforcement learning for the reinforcement learning course. And today we will focus on reinforcement learning and human-robot interaction. So last week we talked about safety in reinforcement learning and how we could integrate a specification, safety specification that was expressed in temporal logics in the reinforcement learning loop. So the idea was that we had that specification, and that was a specification to encapsulate safety aspects, so not to reach unsafe states or not to harm the system itself. So actually, what is really safety, and yeah, what does that usually encapsulate? And also, how would end users of the system define safety? So here, actually, I will start the first part of this lecture with some human-robot interaction definitions about safety, and also how to define and to include the perception of safety by the end users, and then how, given these notions of perceived safety, how can we include that in reinforcement learning? And also then to a broader extent, how can we benefit from human perception and human desires to help in the reinforcement learning processes? And then one problematic is, can humans help the agents learning, and also can the learner and the agent learn from humans? So the intended learning outcomes of this lecture are to understand the differences between the objective safety, the normative safety, and perceived safety, and then I will explain later give definitions of these terms, and then how to apply human notions of safety in the reinforcement learning loop, and also how to include the human in the reinforcement learning process. So some credits here. I took some figures from the literature, and I cite all the what I think relevant literature is all along the slides. Also, a big thank to Ilaria Torre from the division of RPL about some slides I got from her about a lecture on perceived safety that was given at the Safe Autonomy course. That was a course given 1.5 years ago. And also, I drew my inspiration from some talks of Dorso Sadiq and Mohamed Chitouani, who were invited speakers at the RL Conference workshop. So yes, today I want to cover two things. One notion is what is the definition of safety and how safety is perceived by humans, and I will also touch upon some notions of trustworthiness with regards to autonomous systems, which is maybe that first part that is not that much about pure reinforcement learning, but then the second part will be about how to include this in the reinforcement learning loop, and how to bring the human and benefit from human interaction in the reinforcement learning loop. So let's start with some pure human-robot interaction perspective on what is safety versus perceived safety as perceived by humans. Right. So in the previous lecture, again, we saw that shielding was preventing an agent to take unsafe actions, and then a definition of what safety was, what we meant by safety was that actually it was kind of the absence of an acceptable risk and conditions that would lead to harm the people around the robot or around the autonomous system, or to endanger its direct environment and also itself. So what about triggering an action that was overreaching the limits of the system and potentially breaking the system? And actually, this kind of safety, we can take it as a sort of general definition of safety. But actually, there are also some different aspects of safety that we especially consider in robotics and the design of autonomous systems. There are objective safety, perceived safety, and normative safety. So objective safety, which is sort of what we are mostly familiar with, is basically referring to all the tests and controls and also all the algorithms that you can implement in a system to ensure that the risk of collision, of whatever the risk of breaking the system, will be minimized. And on the other side, there is perceived safety that refers to a person's perception of that risk. And for the purpose of that lecture, we will focus on the risk perceived by the people who have to interact with the system in question. So if it's a robot or a collaborative robot, then the people that have to interact with that robot. And then if it's a car, then maybe the people who have to be the passengers of that car, or maybe also the pedestrians in the street who might be in the same environment of that car. And then there is also a notion which is called normative safety, which is basically the collection of best practices and norms and sort of safety assurances that are already in place. So for instance, in the autonomous car industry, whenever you are building a new autonomous car, you're probably starting from scratch, and you have already some sort of norms, let's say also some state-of-the-art sensors that you will embed, and then you will also implement that to integrate in the system. So normative safety is actually a way to ensure that the standards are met, but whether or not these standards work can only be assessed through the objective and the perceived safety. And all these three types of safety have to be met to satisfy the overall and the final safety outcome of the system. Okay, but then let's have some examples of objective safety, and then to put some words and to match some examples to these definitions. So, as we have said, objective safety relates to object-related quantifications of real-world risk, which can be more or less complex depending on a specific system. So, for instance, let's take the risk of collision. For instance, for an autonomous car, you might want to avoid or to minimize this risk. So, what normative safety might say is to add a new sensor to your autonomous vehicle, and a way to objectively measure the safety would be to count the number of accidents the car with that system was involved in versus the number of accidents a car without that system would be involved in, and then compare statistically these two cases, with or without the new sensor. Another example, so imagine that the car has a remote interface, so you can control the car in a remote location, and you can teleoperate the car. So normative safety might say you need to add some sort of encrypted communication or encrypted data storage to the interface, so you are sure that no one will hack and control the car instead of you. And how would you measure objective safety? Is to compare the number of reported issues between cars that have this encrypted communication and cars without. And then another example, last example of a risk that an autonomous vehicle might run out of gas or electricity if you consider an electric car. So what do? Is you might want to improve the path planning of your car, and how you test it is you need to see how many cars need to be towed away after or and before the improved path planning. So this is for objective normative safety, and actually what happens is that many of the systems that we design might have at some point to interact with people, with human beings. And the people who will use these systems are most probably not the engineers who develop the car or the autonomous system. So they might have a different perception. And actually, what happens is that when you deal with people, then you notice that people's behavior is hardly predictable, and it's very, very difficult to quantify or to generalize something that might work for every possible user of the system or every pedestrian in the street. And this is actually what psychology tries to study, to see how people behave and how people think. So then we enter in the fields of user experience, system design, and we can bridge some gap between psychology and engineering. So here, without entering in details, actually what we can say is that people, they rarely follow the optimal or the mathematically optimal behavior. And then an example to see that is that from game theory, there is the dictator game. So you have two players, A and B, and A is called the dictator, and B is just the receiver of the offer. And then let's say that the dictator has a sum of money that will offer that split of this amount between player A and player B, and player B accepts or rejects the offer. So then if player B accepts, then both people, the dictator and the receiver, will get what the dictator offered. But then if player B rejects, then no one, then B doesn't get anything, but only the dictator. So the mathematical models from the game theory that we say that, of course, if you're player B, you should accept any amount that is offered to you. But conversely, I mean, if you're the dictator, you should offer the minimal possible amount, because in theory, the other player will definitely accept anything you give. And in practice, it doesn't happen because people tend to reject what they call unfair offers. So it's really fantastic, but a lot of this is actually happening in a lot of different cultures and countries. People tend to converge to the idea of a fair share. So if the dictator doesn't offer something that is close to 50-50 share, then the people will reject it, even though they could have gained, let's say, any single euro or dollar. So yeah, let's say that we also have another example with autonomous vehicles that time. And some experiments show that people actually behave sometimes quite recklessly around autonomous vehicles because they think that there is no human error involved. So they think that it will be safe. And then there was a study conducted in China that I cited here in the slide that showed that basically other drivers would also kind of bully the autonomous car and behave more aggressively when they are around autonomous vehicles, because they assume that, and they might even challenge the autonomous vehicle, that actually it will take care of avoiding collisions. So therefore, I can go as fast as I want or drive as aggressively as I like, and then probably it will be fine because it's taken into account when designing creating autonomous systems. So yeah, this is also an extreme perception of the safety of the autonomous car by humans, and there are also different scenarios. I mean, what do you think is potentially more complex, an interaction between two autonomous cars and or the interaction between two pedestrians, or the interaction between an autonomous car and a pedestrian? So what is the most complicated and the most challenging from the designer's perspective? Well, actually, it's the one involving the pedestrian, because of course you have to ensure the objective and the normative safety, but you have to be aware that there might be a wild car or a wild pedestrian moving around and might just jump in front of the car, and like kind of adversarial example to see if it stops. And it sounds quite crazy, but it has been shown that people might have these challenging behaviors against the autonomous systems that we deploy. And this is something that we have to take into account in the design, and then also in the learning of optimal policies. All right, so now let's match these examples that we saw before, also with the perceived safety. All right, so for the avoiding collision one, then the normative safety would be to add a new sensor, and this safety is perceived as such by potential users. So you can look at whether they stop in front of the car or whether they believe the system. And actually, it might be tempting from the designer's perspective to add extra alarms or some signal, some alarm that says pedestrian, that the car is approaching or whatever. But then it might also be counterproductive. And not necessary, because people might just be fed up of hearing some alarms when the car is, or any car is approaching, and then do not pay attention anymore. So that might be really counterproductive and maybe more dangerous, because people would care even less. So the other example was the car remote interface, and then perceived safety. Then I mean, actually, we have to look at what people see and how they see the car doing in the environment, and then what would they expect when you change this encryption. And then a final example was running out of fuel. So maybe perceived safety is just about communicating clearly to the user and being transparent about the current level of fuel at all times. Just saying, yeah, oh, maybe at some point we have to recharge fuel. Right, so some human-related characteristics that can influence perceived safety. So in studies, it has been shown that the people's attitudes towards technology is a bias that influence how people perceive safety. So, for instance, you may have users that are generally a bit more in favor of new technology, people that are a bit more reluctant. And then an example is that imagine that you have already ridden in an autonomous car. Then maybe, if it went well, you will be willing to do it again. Previous experience and also age or factors, because typically older people might be less willing to interact with autonomous systems and might feel a bit less safe when they interact with autonomous systems or robots. Also, knowledge is quite important. So the general knowledge about technology is a good factor. Gender is also a factor because just take, especially in the case of the autonomous cars, all the car ads that you see, they are usually directed at men. In fact, it has been found in the literature that women feel less safe in interaction with autonomous systems, and especially cars. And then the capacity to trust. So that could be measured if someone might be willing to go on a car ride or not. And I will talk about trust a bit later. And also cultural background, because most of the autonomous systems actually are tested and deployed in Western cultures. And it has been shown that, in fact, in Western cultures, they are more willing to interact with autonomous systems. This can influence whether people will actually use your system. All right, so now a couple of words about one related notion. And actually, when robot interaction, the notion of trust is also important. Is whether you think and trust that a system will be robust to failures of the system and risk, and whether you hope not to be harmed by the system. And actually, the human element has to be represented a lot when talk about trustworthiness of our systems. That's why it's of utmost importance. And in human-robot interaction, people talk a lot about the good calibration of the trustworthiness of human people in their use of the system. Actually, we will see that in some cases, users, they can have an exaggerated trust in the system, or not trust in the system. And actually, especially in the case of overtrust, this might be a problem, because when you trust too much, about the capacities of the system that leads usually to the misuse or to overuse of the system. So there is, again, in the context of autonomous cars, imagine the autopilot system of the autonomous car. Then in some environments, you assume that you can use this system and then the system will drive the car without the help of any human driver. But the driver is informed that they still need to have their attention on the road and to be able to take control over if the car happens to be in an unexpected situation. An obstacle suddenly arriving on the road that the system would not have time to react or didn't detect them. Then this is usually what is asked to the human driver to be able to emergently brake at all times in case something happens. And even provided with that strong recommendation, then some users just turned on the autopilot and didn't provide the attention needed. And this led to car accidents that sometimes ended up fatally because people did overtrust the system and just let it go. And here is an example also of overtrust. Is that it was during a demo, I think this is a Volvo car, that people just thought that the car would brake, but in fact it didn't. And the people didn't even react when the car was coming. They really thought that there would be emergency brake and would stop just in front of them, but still didn't. And we really see in that video that people didn't even react, which is a typical situation of overtrust. Then the question, did they survive? I think yes, because otherwise I don't think that the video would be available online. So yeah, good chance they survived. All right, so now you might be wondering why I'm talking about this after reinforcement learning course. Well, now you might be wondering, how do we incorporate all these in reinforcement learning? And then actually, ideally, what we would like with all these notions of perceived safety is, what we would like, it would be, some function or some number about perceived safety that says, oh, this is my perceived safety right now, and why not use this as a reward, and then say, oh yeah, now this is what I get. So find a policy that will maximize a perceived safety reward. But actually, this coming up with a score of perceived safety is a little bit tricky, and then this kind of measurements, and actually this is subjective measurements of human-robot trust, they are usually acquired through human automation trust case, and it requires first to identify the antecedents that influence the trust and the perceived safety robot interaction. But here I will just present a couple of explicit and implicit measures about perceived safety. So, first of all, you have explicit measurements of perceived safety that relate to the conscious impressions and the attitudes that people typically have time to reflect on and then to express. So typically things like a questionnaire, and here you could have scales from 1 to 10 about how safe did you feel with interacting with the autonomous car, or an interview to ask people directly why did you feel safe or unsafe when interacting with the car? And then give some more elements, or ask to elaborate on their impressions. Can also be some informal brainstorming, which is useful when this is done at design time of the system. Would be some questions of like, why would you or your grandmother use this system or this feature if we added to the autonomous system? Okay, so these are some explicit measures, and it requires people to be able to express these. And what all people have in common, in opposition to that, is that people have some unconscious thinking about these explicit answers. And they tend to unconscious unconscious behaviors or attitudes. So that can be measured in terms of reaction times. For instance, it would be to ask and to measure how quickly in a questionnaire the people would click. If you do an online questionnaire, that would be what is the time it takes them to click on either the word safe or the word unsafe. And then what you can deduce is that the faster and the quicker they are clicking on the word safe of the questionnaire, then the strongest is probably the association between the safety and their system. Then behavior is assessing human-robot interaction is just to look at them. So if you can record people when they have human-robot interactions or human-autonomous system interactions, then are they smiling when they interact with the system, or do they look uncomfortable? Are they about to cry? These are of course very different outcomes that we can take into account, and also to assess the interaction engagement. Are people willing to use the feature? Are they willing to interact with the system at all? And of course, these implicit measures can be only the analysis of human roboticists after the design of the system, after some trial interactions. All right, but then just keep in mind that there is no sort of general measurement of implicit safety. It also depends a lot on your application, on what kind of system you have, and also what kind of questions you're trying to answer. And so it's very application dependent, because it can range from robots that are not that leading to unsafe actions or behavior, like some nows, to more high risk factor autonomous cars. And then, just a word about the limits of these measures. Then they don't always actually correspond to what people say or to people's behavior. So when people tell you, "Oh, I definitely trust that robot," then sometimes you may look at how they interact with the robot, and you can start to have some doubts about what they say. So sometimes there is a mismatch between what people say and how people look like when they interact with the robots. So then there is And this is actually what comes with humans. And then there is a lot of literature on psychology showing what people do is different than people say. All right, and then there exists some practical tools to measure that, some sorts of questionnaires that are well established to study to perceive safety and to come up with these measurements. And an example of behavioral measures that you can use, for instance, in the domain of autonomous systems is what is called the car technology acceptance model that asks questions about the safety, the trust, the likability, the friendliness, and then you can compress these answers and come up with an overall value for each of the scale, and then it in the end reflects the driver's acceptance of the car, the autonomous system. And then another tool, and then we are touching upon social autonomy and social navigation is proxemics. So when you're dealing with, especially with robots, robots that move around people, then this is an interesting tool. So proxemics, first of all, the definition of proxemics is the personal space that people maintain around themselves. And it has been shown as well that the distance that people keep from a robot should also be the distance that the robot should keep from a human. So then it depends also on the level of acceptability of the robot. Are we familiar with the robot? Is it a robot that is deployed, I don't know, in the public transportation, at an airport, at a shopping center? Or is it a robot that is elderly houses, and then the proxemics of the robots, then they can be aligned also with how people perceive the robot, how can the robot enter the intimacy of the people, or then stay more in the public space one. And then, of course, it's not proxemics are not an exact science, and it depends a lot. It has been shown that it depends a lot on the distances, on the robot type. So the different levels of embodiment of the robot play a big role in the proxemics. So it depends on whether the robot is more anthropomorphic or more machine-like. And then it depends also on the task. So is the task collaborative? Is it a robot performing a task together with the human, or is it just a robot approaching people to provide services at the shopping mall? Or where can I bring you, or whatever? And then, of course, the proxemics they change a lot, and they vary a lot depending on the levels of crowds. So, proxemic rules, they change a lot. Just think about us humans who are in the public transportation, and the way people are close to you, and you will not feel as well or as good depending on whether it's rush hour, like 8 a.m. in the morning, taking the bus, or whether it's like 1 p.m. and then it's more empty. So then maybe you would not accept the safeties there. And then also proxemics, they change a lot depending on depending on the culture. So this notion of intimate space, personal space, and public space, then they either shrink or get extended depending on the culture. So, for instance, typically if you go to Asia, maybe you have already had the feeling that people are quite close to each other, but in fact, it's because it's just cultural notions of proxemics, which is something that has to be taken into account when deriving good policies for control of social models. And then here, I mean, I was talking about proxemics that are based on the robot type. Here is just some advertisement of a study that performed with Ilaria Torre here at the division of RPL about the game of chicken. So then the idea is that you put two people in a collision course, and then the person who swerves first is not to collide, will lose the game. So I mean, we recreated this environment to see whether human people in a virtual environment, because this was done in a virtual environment, whether they would swerve closer when they're facing a more human-like robot rather than a more mechanical-like robot. And then the conclusion of this was that anthropomorphism influences people's trajectories and how people avoid robots and how they move around robots. And then we could draw conclusions about perceived safety and perceived autonomy out of it. All right. So now about some applications of perceived safety and reinforcement learning. How could we include these notions in reinforcement learning? Can we use it in a reward function, or maybe synthesize some shield out of it, and then once it's put in production, then use a kind of shield to filter out perceived unsafe actions by humans. So here I just brought you with this 41st minutes of the lecture, all the bricks for a lecture that Chris will present in 2 weeks about applications of reinforcement learning for safe and acceptable autonomous systems. And then we'll talk about one particular paper where they created shields based on human feedback for perceived safety. And then I was talking about the reward functions and about the perceived safety. And then I will arrive to the second part of the lecture, and then maybe I suggest we have a very quick pause of 5 minutes. Are there questions so far? All right, in that case, all right, so now let's talk about how can we bring the human in the reinforcement learning loop. So usually, I talked about why not using perceived safety directly in reward functions. And actually, reward functions are a good way to specify the objective of a robot. But the problem is that when we want to design reward functions, we need actually a lot of knowledge about the agent, its environment, and so on. So actually, it is extremely challenging. And then, in the context of human-robot interaction, one promising approach actually is to directly learn the reward function from human teachers. And actually, this is called inverse reinforcement learning, which is the field of learning an agent's behavior and an agent's objectives and values or rewards by observing the agent's behavior. So we might observe the behavior of a human in some specific task and learn which states of the environment the human is trying to achieve, and then what the concrete goals might be. So inverse reinforcement learning is the paradigm where the goal of the agent is to find the reward function from expert demonstrations that could explain the expert behavior. Right. So usually in inverse reinforcement learning there are three types of methods, and then I will describe them very quickly. So the first method is the first family of methods is called max margin, that attempts to estimate rewards that maximize the margin between the optimal policy or the expert policy that is learned from demonstrations and all other possible policies you could imagine. And then these methods they actually assume that the reward is a linear combination of features, and will attempt to estimate the weights associated with these different features. So in other words, it's finding a reward function such that the policy would outperform all previously found, all other controllers. So then the other category of second category of inverse reinforcement learning algorithms is the one of Bayesian methods, which have two defining characteristics. The first is that the optimization process usually maximizes the posterior distribution of the reward, and the second is to use the prior distributions of the reward in order to define that posterior distribution. So one advantage of these methods is to convey some prior information about the reward to the learning algorithm through prior distribution already observed. And these techniques, they consider experts' action as the evidence used to update the estimate of the reward function. And then the third category of inverse reinforcement learning algorithm is maximum entropy methods. And these methods are usually defined by using maximum entropy in the optimization of the estimate of the reward function. And usually these methods they are known to be good as easily extensible to continuous space, and can also address suboptimal expert demonstrations or sometimes noisy demonstrations. But Bayesian methods can also handle that, and I will give some examples. All right, so now if you consider domains like robot learning and human-robot interaction in general, here there are some possibilities for the robot to collect some examples of how a human wants the robot to act and to respond. So, okay, imagine teaching an autonomous car to drive safely along human-driven cars. So during training, you show that you would like to merge in front of other vehicles, and the autonomous car would learn from these demonstrations and try to follow your examples as closely as possible. But then, when the car is deployed, it might become an aggressive driver that behaves differently than anything the robot has seen before. So matching your demonstrations might cause, or matching the demonstrations unintentionally might cause the autonomous car to have an accident. Actually, when learn from the demonstrations, then we need to provide demonstrations for every possible situation. That might be one of the limitations of only learning from demonstrations, because then it might be difficult to find a policy, or might be difficult for the robot at all to accurately generalize the knowledge learned from just a few expert demonstrations. And actually, what ideally we would like is the robot to use some human teacher and some information provided by the teacher, but a bit more intelligently. And then that's nice, because of course we have these demonstrations from data that we can get in a passive and offline way, but we can also collect some preferences from a more active way, and asking the human expert, oh, do you like this or that demonstration? And then, of course, all these data sources, either from demonstrations or collecting and curing human preferences, they provide information about the human's true reward function. That is what actually we want to extract. All right, but then let's first start with learning from human demonstrations, and then after that I will cover active learning and how to query the human to include preference of humans to help to recover the reward function. So here the problematic with learning from human demonstrations is, could human help the agent's learning, and could the agent learn from humans? We are still in that problematic, and basically here for learning from human demonstrations, we consider a set of demonstrations that are recorded. So here we have that example that comes from the group of Dorsosadik. With a roboticist in Stanford, and then we have this autonomous arm that to grab and to perform some movements in the space, and we want to learn some good demonstrations, some good policy for that. And here basically, so we have some demonstrations from human that we get from teleoperation. So here you see that actually the demonstration comes from a human teleoperating the robot to achieve task in a proper way. So we have these demonstrations from human, and we assume that there exists a reward function that is basically a linear combination of features, and assume that these features we know beforehand, and that we also know some continuous control policy of it, and that we also know the dynamics of the robot. So in fact, to learn, so since we have we already know what are the features that are involved in the reward function, then actually what we want is only to learn these parameters that we have here. So the weights of the different features. So okay, given these demonstrations, then what is possible to do, and then I refer to these two papers that are cited as footnote, is that actually what we now can do is to derive a distribution over that weight vector for the different features of the reward function that will best explain the human's demonstrations. And then we will do that via some Bayesian inverse reinforcement learning approach that require a probabilistic model of the human demonstrations and some prior over the weight vector for the reward functions feature. And we also assume that the demonstrations, they are independent conditionally to the weight vector, and also identically distributed. And then also one specific thing about it is that we are learning from human demonstrations, and we assume also that the human is trying to maximize its internal idea of what the reward function is. But actually, because we are doing it with from a human demonstration, it might be the case that actually the human is inaccurate in its execution of successive actions. So actually, the demonstrations are maybe noisy, not perfect, or inaccurate, and actually we need to express how the human demonstrations are noisy, and then we have to account for this human noisiness, and this is typically done using a Boltzmann distribution, which is a distribution over the trajectory space. The trajectory space and what the sequence of actions can look like. This is a distribution over this space, and also with respect to the true reward of the trajectory. And here you see some parameter here is called in the Boltzmann distributions the temperature hyperparameter. It's also called as rationality coefficient, and actually it captures the level of human suboptimality and when providing and receiving these demonstrations from the human. And then, since we have your information, then the weights of the features of the reward function, they are derived with Bayesian updates, and we end up with then an estimate of the reward function that is directly from human demonstrations. Right. And so just before I just I mentioned preference learning, and then preference learning is actually the idea of asking the human, do you prefer this or that execution of the system? So just here a very quick word on active learning. So active learning is in computer science the fact for a learning algorithm to have an hypothesis model of a solution and to query a teacher, which here would be a human, whether an element belongs to the solution. And then the teacher will say yes or no, or maybe also provide some score on how much the element in the solution belongs to it. Right. So so here let's talk about active learning of reward functions. And instead of learning from a batch of demonstrations, then here the idea would be to let the robot calculate and show two trajectories by itself. So no one here would be teleoperating the robot or creating the demos. Instead, the robot will randomly generate two different trajectories. And the only type of feedback that we are getting from the evaluating human is whether he prefers they prefer one or the other trajectories. So this is helpful to learn something about the underlying reward function that exists as well. And in fact, we consider that the human has an underlying reward function again that the robot has to try to optimize, and this is again considering reward as a linear combination of sets of features and weights. So here credits to Dorsa's Alex talk because I'm taking most of her pictures here and also some of the explanations. So if we imagine that this weights vector lies in a three-dimensional space, because here we're having these 3D trajectories, then the true reward function falls somewhere between that goal. So this is maybe this point, or any of these other points. So then, when every query that we ask from a user, every query will generate this hyperplane in the space, and then the human response to the question whether they like this or that trajectory, then it will tell on which side of the hyperplane the true reward function will fall. So this is basically for one single query, and of course, like for the learning from the set of demonstrations, we consider human noises. So there is still this use of the Boltzmann rational noise model. So we are not completely removing the wrong side of the hyperplane, but then rewriting these samples. And then the interesting research question here is, what is the sequence of most informative diverse queries we can ask a user to quickly learn the reward function in a data efficient way? Because what ideally we would like to is to save queries too close to the user, because generating and executing these queries might be expensive, and depending on the applications, it might be time consuming to just execute the complete sequence of actions and trajectory, and also because human feedback is expensive. You literally ask a human to be next to a robot and to label this or that execution of the system. So it implies that you have human annotators, and human annotators is a scarce and expensive resource. So to efficiently synthesize these queries in the active learning framework, then what we want to do is to optimize some information theoretic type of objective. So we want to find a set of scenarios, and that would be the 5 here, that correspond to the different scenarios that are shown to the user, and we want to find the scenarios such as we are maximizing the minimum volume that would be removed from this hypothesis space that I showed. So if you remember that space with that ball, the different weights, then this was representing the different reward functions that we could have. And what we would like is to ask the human the set of scenarios that would correspond to hyperplanes by asking in a way such that we would remove as much as volume as possible. So to refine the idea of the reward function. And then we can quickly converge to the true reward function we would like to get. So this is a volume removal objective that we can get with module optimization or information gain, which is also nice information gain because that could also incorporate the human uncertainty in responding to the queries and so on. And then we can also make sure and also enforce the set of constraints that make sure that the scenarios we are generating are realizable under the robot, and of course that they satisfy the dynamics. And then that relates back to breaking the robot by asking and showing unfeasible queries. And then now, if we have to integrate the learning from demonstrations and from preferences, then actually, in what order should you leverage the demonstrations and the preferences? So, the demonstrations they provide high-level information, while the preferences some very isolated aspects of the human's reward function. So it seems that actually we should start by the high-level demonstrations before probing low-level preferences. And actually, they could also come up with some proofs to say that actually this is good to first start with learning from demonstrations, and then to go refining the reward function with the set of active learning queries. And the idea is that when you generate these queries, prove that the robots will gain at least as much information about the human's preferences as any other order of demonstrations and queries. Yes, and I think it's also a very, this this paper is also a nice nice way of integrating this learning from demonstration and also from queries to learn reward functions from humans. So I can really recommend this as a literature. All right, so 4 minutes left. Okay, so I have 2 other pointers about HRI and reinforcement learning. This is really a recurring and hot research topic these days, so there is a lot going on in the field. But maybe I can just cite that one, which is considering providing instruction signals that indicate to the robot which action has to be performed in a given situation. And the fact is that the instruction signals, they are not labeled, actually. So if interacting with a robot that has to learn a task, I say this or that, then there is no label. It's just an abstract way of signaling the robot what is my desired instruction to the robot. So then this work is going along these lines as first transferring the information about the optimal action between several task states, and then states that are associated with similar instruction signal will contribute to interpret the meaning of that signal, and then in turn contribute to learning the optimal action. So this is used to accelerate the learning process. And there are like two different problems, sub-problems: shaping and interpretation. So interpretation is basically the low-level mapping between instruction signals and actions, and shaping constraints between basically using the interpreted instructions for accelerating the learning process. Yeah, this is another interesting line of work. And then this final line of work is about social navigation, and was considering adapting the motion of some robotic assistant rollators for people with disabilities. And then this is about developing methods that take into account the variability in walking, and also adapting the robot's platform to the motion of the humans. So this is an online motion adaptation, which was using some model-based reinforcement learning. So yes, I have the impression that I'm running out of time. Yeah, so as a conclusion today, we covered and we discussed about perceived safety and how humans have notions of safety. You will see in the next lectures applications of perceived safety to shielding. So Chris will be presenting these lines of work and a paper that he had written with interesting experiments. And then we also talked about reinforcement learning from human demonstrations and also actively learning reward functions in an inverse reinforcement learning context. So this is the end of my lecture. I'm happy to take any questions now or offline. Do not hesitate. And these are the different references. There's a bunch of references about PRC safety, also the proxemics, and this last slide is about mostly about the demonstration learning and active learning, human preferences. Yeah, thanks for following today's lecture, and hope to see you soon. So have a good day still, and yeah, class is dismissed for today.